close. So because it's the last lecture of the semester, I'm actually going to do a phrase of the day today, right? Instead of a word of the day. So you'll get a bonus point for each word in the phrase. Right? So be on the lookout for that, or keep your ear out for that. It's coming pretty soon. All right. So anyway, let F equal P times I plus Q times J. All right, that's the model for a vector field of an open and simply connected region D. All right. So simply connected regions are ones, I mean, if you think about continuous functions in 2 dimensions, simply connected regions are the analog for 3 dimensions and beyond, right? So there's no gaps, there's no weirdness, it doesn't twist around upon itself or anything like that, right? So if that's the case, then P and Q would have continuous first order partial derivatives in D, and those partials would be equivalent to each other, specifically partial P with respect to Y and partial Q with respect to X. If that's the case, that was a typo that somebody pointed out, lowercase t, and just grammatically, there should be, and if P and Q have continuous first order blah, blah, blahs, then the vector field is conservative. All right. So if you can show that the first order partials are equivalent to one another, then essentially you're determining that it's a conservative vector field. All right. So and that's really just a working definition of a conservative vector field. It's just a vector field that follows this relation. All right. So when we're determining whether a vector field is conservative, all we're doing is we're looking for the P value and we're looking for a P equation and looking for the Q equation and find the first order partials associated with that. Now, P and Q, because F is representing a vector field, and those vector fields are basically representing directional derivatives, which in turn are gradient values. P and Q actually make up the gradient of F. Right? So note, the gradient of F is equal to P comma Q. All right. So, but at this point, we're just identifying the function P, multivariable, x squared minus yx, and the function Q, y squared minus xy. And we're finding first order partials with respect to y. So basically, with respect to the other functions, mean variable. All right. So kind of looking back at this concept of the gradient of F is really, based on what we know, we would denote that as partial F with respect to X, partial F with respect to Y. So this is indirectly saying that P is the first order partial with respect to X of the original function F, which is defined as a vector equation. All right. One of our goals is going to be to pull functions out of vector equations. I'm sorry, pull functions out of vector fields or vector functions themselves. All right. So simple polynomial-based functions, or trigonometric or whatever, but something that is multivariable rather than a vector value. All right. So if I differentiate this with respect to y, which is easily done, it's just negative y. That's not the real thinking part here. What I'm actually doing is taking the second order mixed partial. This is the same as saying, I'll use the other notation, F sub x comma y. when I find the partial with respect to x of q, I also get a negative y. This is saying, or saying the same thing as the mixed partial yx, f sub yx. All right, these two things should be the same if we're going to say that the original function is, I mean, if you think back to partial derivatives, we're talking about continuity for a given function. If we said if the function of whatever it is, multivariable function, is continuous, then the mixed partials would be equivalent to one another. Right? And so that's what's happening here, except our original function is defined as a vector function. Right? So it wasn't given as a multivariable function. Now it is a vector function with multiple variables, but it's not in the form that we were used to in the previous unit. Right? So this is another way of looking at that. Right? But because this is kind of rounded in something that's familiar to us, we know that the second order mixed partials should be equivalent to one another. If they are, then that's a good thing. That means that there's validity to what we're doing. But we're now just giving a name to that, right? So what we would say is, therefore, f is a conservative function. So let's say conservative. Right. So, you know, they can be a little bit more complicated, but I'll show you where this is going in a couple of minutes. Oh, probably. Let me take a look. Oh yeah, I got it all turned around and inside out. So with respect to y, this should be, yeah, right. So negative x. So this one goes away, and this one just becomes the coefficient of the y. Then this one, with respect to x, this one goes away. This goes to 1, so this is negative y, so this one would be not conservative. Thank you. All right. So the next one, a little bit more complicated in terms of its appearance, but same idea conceptually. So p is 2x e to the y, xy, sorry. X squared y e to the xy, that's fun. Q is x cubed e to the xy plus 2y. So we're finding partial with respect to y, partial with respect to x. And that'll give us our mix, our second order mixed partials. And once we find out whether or not those are equal to one another, we'll determine whether this function is conservative. All right, so with respect to y, this constant multiple is going to stay put, so 2x. You hang on to the e to the xy multiplied by the derivative of the exponent with respect to y, which would be x. All right, I lost my plus sign in here. Let me just kind of smidge that over. Otherwise, this would be kind of a juicy problem. I don't know what song this is. But anyway. Now this one, again, with respect to y, the x squared is going to be constant multiplier, so we can hang on to that. But then I have to take the derivative of this part of it. I'll use my highlighter here. Using the product rule, I'm going to be looking at the first function, y, times the derivative of the second, which is e to the xy times x with respect to y, plus the second function times the derivative of the first. All right, so e to the xy, derivative of the y would go to 1. All right, so I can clean that up a little bit. the tendency is to say, well, let's clean it up by factoring out the e to the xy. You know, we can factor it out of the whole thing, or we can just roll the dice and hope that q kind of works out the same way or not, you know, to determine whether it's conservative. All right, so I'm going to, you know, because we have, like I said, a common e to the xy, I can pull that out. I'll rewrite the first part, 2x. Well, let me clean that up too. It's 2x squared because I can consolidate these two. E to the xy plus x squared e to the xy. When I pull those out, it looks like I have yx plus 1. And then I can go even further if I think it's helpful. I see that I have a common x squared, common e to the y. Let's come out of the whole thing. So I'll have a 2 left over from this piece plus yx plus 1, which would be x squared e to the xy times 3 plus yx. I don't know how much of that was necessary. Correct. But I want to give myself as many options as I can when trying to figure this out, or at least this part of it. Now, when I take the derivative partial of q with respect to x, I'm going to have another power rule kind of situation on my hands. So we'll take care of that right from the word go. And so x, so the first would be x cubed times the derivative of the second, e to the xy, times the derivative of the exponent with respect to x would be the y, plus the second. Again, we're using our power product rule, e to the xy times the derivative of the first, 3x squared, plus 0, because the two y's are just going to go to 0. All right. So I have my common factors here. I got an x squared, and I got an e to the xy that could be pulled out. I won't be able to pull out all of the x cubed, but I can pull out an x squared e to the xy. So that would make this into just an x. I still have the y. And then over here, I just have the plus. There's only a 3 left over, so plus 3, which happens to be what the other side is, you know, commutative property notwithstanding. So therefore, I would say, therefore, f is conservative. All right. So it's really as simple as that to determine or really conservation of functions. Vector fields anyway. All right. So let me stop this recording.